Okay, thank you. Ladies and gentlemen, good morning. My name is Sirui Chen. I'm from Zhejiang University, China. Today, I'm excited to share our latest research, SIGformer. It is a sign-aware graph transformer for recommendation. This work is jointly completed by researchers from Zhejiang University, Huazhong Agricultural University, and Bohao. Recommender systems are a type of information filtering system that predict user preferences based on user historical interaction with items. Graph-based recommender systems use graph structures to make recommendations. In these systems, users and items are represented as nodes in a graph, and the interactions between users and items are represented as edge. Most existing graph-based recommender systems can only handle on-site graphs, which means they only use the positive feedback within the graph, while the rich negative feedback is directly removed. However, negative feedback in recommender systems contain rich information. In addition to direct user item preferences, higher order paths containing negative edge also conveys useful collaborative insights. For example, in this signed graph recommender system, this path U1, I2, U2 suggests that user 1 and user 2 may have similar preferences because they both give negative feedback to item 2. And the path U3, I4, U4 shows that the different preferences between user 3 and user 4. While the longer path from U1 to I3 passing I2 and U2, it implies that user 1 is likely to favor item 3 because his similar user U2 has previously interacted with it. There have been some efforts to incorporate inactive feedback in recommendation systems. However, they all face two limitations. First, this work separates positive feedback and negative feedback into two independent graphs and process them separately. It means they lack a holistic consideration of both positive and negative feedback. And the collaborative information we mentioned in previous page is also difficult to capture. Second, existing sign-aware methods all use MLP or GNN on the negative graphs. However, most graph neural networks, especially those designed for recommendation, are built on the homophily assumption. Homophily assumption states that the connected nodes are more likely to be similar. But in signed graph, when there is a negative edge, it means that the nodes at both ends have different characteristics. This goes against the homophily assumption. Moreover, using MLP makes it hard to make full use of the graph structure, and it is a challenge to chain effectively with sparse data in recommendation. Inspired by the success of transformer in different fields, we propose a transformer-based recommender system. Transformer estimates the similarity between nodes based on their historical interaction information, then aggregates information from the similar entities for prediction. This process highly aligns with collaborative filtering in recommendations. We also designed two new positional encoding. One captures spectral information of signed graph. We call it sign-aware spectral encoding. The other one captures pattern information between a pair of nodes. We call it sign-aware path encoding. For the sign-aware spectral encoding, we start by using a parameter called alpha to combine the Laplacian matrix of the positive and negative graphs, forming the Laplacian matrix of signed graph. Next, we decompose the Laplacian matrix and keep DH eigenvectors with the smallest eigenvalues. As shown in the figure, tilde H is an n by DH matrix. Vertically, it is DH eigenvectors, while horizontally, it represents the sign-aware spectral encoding of each node. Multiplying the spectral encoding between nodes forms an n by n matrix PS, which is the sign-aware spectral encoding of SIGformer. Here, we use a positive parameter, theta, to scale the matrix. Theta is a learnable parameter. The result of spectral encoding PS is added to the attention weights in the transformer, as shown in this figure. In our paper, we prove that when left multiply V by PS, the sign-aware spectral encoding designed in our manner is equivalent to a low-pass filter. It can minimize the expression in lemma 1. The detailed proof is provided in the appendix of our paper. Based on lemma 1, when alpha is greater than 0, the low-frequency components we use as spectral encoding have the effect of pulling nodes connected by positive edge closer together and pushing nodes connected by negative edge further apart. And for the sign-aware path encoding, we consider all paths with a length not exceeding the threshold LP. By enumerating the path length and the sign of each edge along the path, we obtain NP different path types. Subsequently, we map each path to a learnable value, forming an NP-dimensional vector phi. As shown in the figure below, the path relationships between nodes U2 and U3 form the vector OU2U3. The third element of O being 1 indicates there is one path of pattern 3 between these two nodes, while the first element being 0 signifies the absence of pattern 4 path. We multiply the transports of O and by the learnable vector phi, obtain a scalar P. This scalar represents the number of each type of path between these two nodes. We aggregate the p-value for all pair of nodes into the matrix PP. Therefore, sign-aware path encoding captures the information of paths between nodes in the graph, forming an n by n matrix. And the results of path encoding are also added into the similarity weights of the transformer, as shown in the right figure. In summary, we have devised sign-aware spectral encoding and sign-aware path encoding, and integrating them into the transformer. The details are illustrated in the diagram and the formula. Given the large number of nodes in recommendation systems, taking all node pairs into calculation attention is expensive, so we employ a random walk sampling strategy. For each node V, we sample neighbors within LP hope by conducting random walk starting from V, forming a node set. We call it SV. And in the formula, the yellow one is the attention weight in the original transformer. The blue one is the spectral encoding. MVW signifies the dot product of the spectral encoding vectors of V and W, which can be pre-computed without chaining. And theta is a learnable parameter. The green one stands for the path encoding. TVW represents the pattern of paths between two nodes during random walk. In this way, the time complexity of our attention module is reduced to the number of nodes n plus m, multiply the number of embedding dimension d, then multiply the average number of nodes sampled per node. Following are the experiments results. We conducted experiments on 5 real-world data sets, and the result indicated that our methods outperform existing methods. Here are the ablation study. First, performance decrease when negative edges are removed. It indicates that our model can utilize information from negative edge. Second, removing each type of encoding separately results in a performance drop. It shows that the effectiveness of two encoding in our model. The figure above shows the relationship between model performance and parameters. LP represents the threshold of length, while alpha is the parameter in spectral encoding that controls the strength of negative feedback information. As these two parameters increase, the model's performance shows a trend of initially increasing and then decreasing. The table below shows the learned values of the learnable parameter phi for different path patterns of length up to 4. The left table shows the top 5 phi values, while the right table shows the bottom 5 phi values. Paths with larger phi indicate higher similarity between the nodes at birth ends, and we can see that these paths in the table A often have an even number of inactive edges. Also, paths with smaller phi suggest a lower similarity, and these paths in the table B often have an odd number of inactive edges. Finally, we make a short summary. SIGformer is a sign-aware recommendation system based on graph transformer. It has two types of positional encoding. One captures spectral information of signed graph, called sign-aware spectral encoding. The other one captures path pattern information between node pairs, called sign-aware path encoding. Moreover, we prove its effectiveness and the rationale behind SIGformer through various experiments. Our code is now available on GitHub, and we welcome you to check it out. That's all. Thank you.